Next is about the laws of reflection. We have studied what is meant by reflection. What is a reflection? The optical phenomenon in which a light ray incident on a reflecting surface will come back into the same medium is said to be the reflection. Now, what are the laws of reflection? We have to study then. Regarding the laws of reflection, we are having two things. One is said to be the first law of reflection, and the second one is second law of reflection. To understand the laws of reflection, let me draw that ray diagram once again for reflection phenomenon. So, here this is called the interface and nothing but a plane which is separating the two optical media, and this is the normal line which is perpendicular to the interface. This is the normal line, whereas this is the interface. Interface is nothing but what? Of plane surface which is separating the two optical media. This is optical medium 1 and this is optical medium 2. For instance, let me treat this is air and this is glass coated with silver. That means it is acting like a mirror. Mirror is an example for reflecting surface, a plane mirror I am choosing. Now, a light ray is incident on this, like this, a light ray is incident here. Once again I am drawing it. So, you must be cautious while you are drawing the ray diagrams. Please maintain straight lines only. So, this is the incident light ray, and the point where the light ray is incident is said to be the point of incidence. The point where the light ray is incident is said to be point of incidence. And now, this light ray is reflected like this. This is the reflected ray. This is incident ray, and this is reflected ray, Now, here there is an angle between incident ray and the normal line which is called as angle of incidence, and here there is an angle between the reflected ray and the normal which is called angle of reflection, and this is what? The interface. This is said to be the point of incidence. The point where the light is incident is said to be the point of incidence. Now, what is the first law of reflection says? If you see here, this incident ray PQ, the reflected ray QR, and the normal line, all the three are lying in the plane of the board. PQ is in the plane of the board, normal line is in the plane of the board, and reflected ray is also in the plane of the board. That means, the incident ray, the normal line and the reflected ray will lie in the same plane. This is called as first law of reflection. What is first law of reflection? Incident ray, comma, normal line, and reflected ray will lie in the same plane. This is called as first law of reflection, and with a small experiment also we can check this first law of reflection. Just take a white sheet on a cardboard. You take a white sheet on a cardboard, and over that white sheet you draw two perpendicular lines like this. Let me take, this is a white paper which is placed on cardboard, and draw a line like this and like this. So, now you take a laser light source of a single color and keep it in the plane of paper like this from one side, or from here, it is your choice, anywhere you can keep it. You take, this is now here you place a glass slab. Here you place a glass slab, and or a mirror you place, the glass slab coated with silver, or this is a mirror you place here. This is a mirror, I am keeping it like this. Okay. Now, you draw a line in this way and maintain this angle as some 45 degrees or 30 degrees or anything of your choice. You maintain some 45 degrees and draw one more line making the same angle 45 degrees with the same normal. Now, these are the geometrical lines what I have drawn. Now, what I am doing, here I will place a mirror, and now I will take a laser source and I will keep it along this line. Now, the laser light moving along this line after falling on the mirror will definitely go like this. If you see here, this and this will be in the plane of paper only, and even the normal line is also on the plane of paper, which says that the incident ray, normal line and reflected ray, all the three are lying in the same plane. This is called as first law of reflection. And now, second law of reflection. What the second law of reflection says? It's a very important one. That is, I am writing it mathematically here and you tell the second law. What I have written here, this is angle I is equal to angle R. That means angle I means angle of incidence is equal to angle of reflection. So, what the second law says? Second law says that the angle of incidence is always equal to angle of reflection. According to the second law, what I can say, the angle of incidence is always equal to the angle of reflection. And these are the two important laws regarding the laws of reflection, and these are the laws which are applicable for any kind of reflecting surface. There is no condition that these laws will be applicable only for plane surfaces. These are applicable for any kind of reflecting surface. That means whether it is a plane surface or a curved surface, whatever may be the kind of reflecting surface, these laws will be valid. Okay. So, what the first law says? According to the first law of reflection, the incident ray, the normal line and the reflected ray will lie in the same plane, and second law says that the angle of incidence is always equal to the angle of reflection. Suppose if I say the angle of incidence is equal to 38 degrees, what will be the angle of reflection? Then angle of reflection is also equal to 38 degrees only. Is it clear? Whether it is a plane surface or a curved surface, these laws are truly valid. Now, this is about the laws of reflection. Now, taking the laws of reflection into consideration, I will consider the two kind of reflecting surface. One is a plane surface and the other is a curved surface or a spherical surface. Now, let me take, this is a plane reflecting surface. This is a plane reflecting surface, and now on this plane reflecting surface, let me consider this is a plane reflecting surface. On the plane reflecting surface, let me consider a parallel beam of light is incident. What kind of beam of light is incident? A parallel beam of light is incident. A parallel beam of light means what? If a beam means a group of light rays. If the group of light rays are parallel, then it is said to be a parallel beam. Now, I am choosing a parallel beam of light which is incident on this. Let me choose, this is a parallel beam of light which is incident on the plane reflecting surface. Here, this is incident here and this is incident here, this is incident here. Now, this is a parallel beam. Now, at the point of incidence, we need to draw what? Normal lines. This is the normal line here, this is the normal line here, and this is the normal line here. Now, as the beam is parallel, these angles must be same. So, this angle is, if it is angle of incidence I, this is also I, and this is also I. Okay. Now, according to the law of reflection, angle of incidence must be equal to angle of reflection. Therefore, this will undergo reflection and it will go like this, and this will also go like this, and this will also go like this. If you see here, these three are parallel to each other and these three are parallel to each other. That means this is what kind of beam here? This is incident beam. The beam is incident beam. Incident beam is parallel beam. Incident parallel beam. Incident parallel beam. And this is what? Reflected parallel beam. Reflected parallel beam. That means when a parallel beam of light is incident on a plane kind of reflecting surface, then the reflected beam is also parallel. According to laws of reflection, if this is I, the reflected angle must be I. So, this is also I and this is also I. Therefore, I can say that when a parallel beam of light is incident on a plane kind of reflecting surface, then the reflected beam is also parallel. Now, I will be considering the curved mirror. Curved mirror I am considering. Let us consider this is a curved mirror. This is a curved mirror I am choosing, as it is a mirror, it should be silvered on one side. Let us consider this is silvered like this. This is the curved mirror what I am choosing. Now, incident the parallel beam. Incident the parallel beam. Now, let me choose this is a parallel beam. This is a parallel beam. Now, a parallel beam is incident, but here how to draw the interface for this at the point of incidence? If you want to get the interface, just we need to draw the tangent at that point. So, at this point this is the interface, the tangent will indicate the interface, and this is the tangent here and this is the tangent here. Now, for the tangent draw the normal line, draw the normal line. So, normal line will be like this, perpendicular to the interface is normal line. Here this is the normal line and here this is the normal line and here this will be the normal line. If you observe here, the normal lines are not parallel to each other, yes or no? Therefore, this angle is I1 means this angle is some I2 and this angle is some I3. So, the light rays, though the beam is parallel, but the incident angles are different here. Therefore, according to law of reflection, if this is I1, the angle of reflection must be I1, therefore, it will go like this. And here it will go like this and this will go like this. So, finally, if you see here, this is I1 means this is also I1, this is I2 and this is I3, because angle of incidence should be equal to angle of reflection according to laws of reflection. If you see here, the incident beam is parallel, but the reflected beam is not parallel, yes or no? So, this kind of reflection is said to be the diffuse reflection or irregular reflection. So, here incident parallel beam we have, incident parallel beam we have, but the reflected beam is not parallel beam. Non-parallel reflected beam, non-parallel reflected beam we are having. Okay. So, from this what I can say, this is a reflection phenomenon and this is also a reflection phenomenon. In this case we are having a regular kind of reflection, but here we are having an irregular reflection or diffuse reflection. This is said to be regular reflection, and this is irregular or diffuse reflection, diffuse reflection. Is it clear? So, what is a diffuse reflection? When a parallel beam of light is incident on a curved mirror or a spherical mirror, the reflected beam is not parallel, which says that the reflected light rays are diffuse or irregular, hence the name irregular reflection. Is it clear? This is about the types of reflection what we are having. But whether the reflecting surface is a plane surface or a curved surface, the laws of reflection will be obeyed. That means incident ray, normal line and the reflected ray will lie in the same plane. The angle of incidence is always equal to the angle of reflection for all kind of surfaces. Is it clear? This is about the reflection and the types of reflection. Is it clear? And now we will study about the a small example I will give you regarding the reflection, how the images will be formed by the plane reflecting surface we will discuss. Then we will move to the curved type of reflecting surface or spherical reflecting surfaces. Next is formation of image by a plane mirror. We will see how an image will be formed by using a plane mirror. For that, let me choose a plane mirror like this. This is a plane reflecting surface. So, this is the silvered part of the mirror. Now, here I will draw a line which is normal to the mirror in this way. This is the normal line, or on this line I am going to keep a point object, a point illuminated object I am going to place. This is a point illuminated object O. This is a point illuminated object O. From the illuminated object, let me choose a minimum of 2 light rays which are traveling towards the mirror. Suppose if I want to form the image, then a minimum of 2 light rays are required. You can take more than 2 light rays, but a minimum of 2 light rays are required. In order to understand how these images will be formed, we need to learn about the sign conventions that we are going to adopt either in the reflection phenomenon or in the refraction phenomenon. So, I will tell you the sign conventions also here while we are dealing with the reflection and refraction. We are going to follow these sign conventions. And what is the type of sign convention we are using here is Cartesian sign convention or rectangular sign convention. Cartesian, C-A-R, Cartesian or rectangular sign convention. Rectangular sign convention we are adopting. What is these? What are these sign conventions? We'll see. This is a very simple sign convention. According to the present mathematical part, we can go with sign conventions like this. If you take, this is the x axis and this is the y axis. This is treated as the origin of the coordinate system or Cartesian system. In mathematics, we will be calling it as Cartesian system. Now, we will make every observation or every measurement from the origin or the reference point. Here the reference point is this. This is the origin or the reference point. Distances measured in this direction will be taken as positive and the distances measured in this direction will be taken as negative. Similarly, distances above this axis is taken as positive and below this axis is taken as negative. Okay. So, what are the Cartesian sign convention says means all the distances are to be measured from the pole. All the distances are to be measured from the pole. This is one of the most important thing. What is meant by a pole? A pole is nothing but the geometrical midpoint of the mirror is said to be the pole. So, this is said to be the pole. Pole is nothing but the geometrical midpoint of the given mirror. The geometrical midpoint of the given mirror is said to be the pole. If you see here, for this mirror, this will be the midpoint. Hence, this is taken as the pole. So, what is the first sign convention we have to adopt is all distances must be measured. All distances must be measured. Must be measured from the pole. Measured from pole. Whether you are dealing with reflection phenomenon or refraction phenomenon, the same sign convention we are adopting. All distances must be measured from the pole. Pole is nothing but what? The geometrical midpoint of the mirror here in this case. Second thing, distances measured in the direction of light ray are taken as positive. In this one, let me take light rays traveling from negative x-axis to positive x-axis. Then distances measured in this direction are taken as positive. Distances measured opposite to light ray. This is light ray I am choosing. If light ray travels from left to right, then distances measured in the direction of light ray are positive. Distances measured opposite to light ray are negative. Distances measured in the direction of light ray, in the direction of light ray are positive. In the direction of light ray are positive. And distances measured, third point, distances measured opposite to light ray, are taken as negative, And next one is distances above the principal axis is taken as positive and distances measured below the principal axis are negative. Distances above principal axis are positive and below principal axis are negative, These are the important sign conventions that we are adopting. It's very simple. Above this axis distance are positive, below this axis distance are negative. Distance measured in the direction of light ray or positive, distance measured in a direction opposite to light ray. Light ray going like this, if you measure the distance like this, it is negative. Light ray going like this, if you measure the distance like this, it is positive. These are the sign conventions we are adopting while we are dealing with the reflection or with the refraction phenomenon. In this case, I can take this is the principal axis. Now, on the principal axis, I am keeping a point illuminated object. From the point illuminated, in order to construct the image, we need to consider a minimum of how many light rays I told? 2. Now, this is the normal line here. Now, let me choose one light ray is traveling along the normal line. If a light ray travels along the normal line, what is the angle of incidence? Angle of incidence is the angle between dash and dash. Angle of incidence is the angle between incident ray and the normal line. Yes or no? This is angle of incidence. Suppose this is incident along the normal line. What is that I value? I is equal to 0. If I is equal to 0, then R must be 0 because I is equal to R. Therefore, the reflected ray should come like this. And I will choose one more light ray which is incident like this. This light ray is falling on the mirror at this point. At this point, you just draw the normal line. Just draw the normal line like this. Now, if you draw the normal, if you have drawn the normal line like this will be the angle of incidence. Now, according to laws of reflection, angle of incidence must be equal to angle of reflection. Therefore, the reflected ray will go like this. This is the reflected ray. This is angle of reflection which is equal to I. Now, here these are the incident rays. So, what kind of beam is incident beam? Diverging beam. As they are diverging, the incident beam is diverging. And this is one reflected ray and this is another reflected ray. The reflected beam is also diverging. Yes or no? But if you extrapolate this reflected ray in backward direction, so you can see that this reflected ray, when you extrapolate in backward direction, it will meet the principal axis at this point. So, by geometry if you see, this and this being parallel, if this is I, this must be I. This angle and this angle must be I because they are alternative angles. If there are two lines like this, if this is I, this must be. If this is theta, this must be theta. So, here this and this are parallel, therefore, this being I, this must be I. Similarly, this being I, this must be I. Okay. Now, this distance is said to be the distance from pole to the object is said to be the object distance. You can take it as U. U refers to object distance. U refers to object distance. And here, this is the distance from pole to the image. This is the point where the reflected rays will either really meet or appears to meet. So, here this is one reflected ray and this is another reflected ray which they are appearing to meet here. They are not really meeting there. So, the point where the reflected rays will meet or appears to meet will give the image. If they really meet, they will give the real image. If they appear to meet, they will give the virtual image. So, in this case, at this point, the two reflected rays are not really meeting, but they are appears to be meeting. Therefore, this point is nothing but virtual image. So, this is which image we had? Virtual image we had. Virtual image. But the object here is a real object. So, plane mirrors will form which kind of images? A plane mirror will form a virtual image for a real object. Suppose if you are standing in front of a mirror, you are able to see your image. Your image is a real image or a virtual image? Your image in the mirror is a virtual image but not the real image. Okay? Because real images can be caught on the screen. So, here the image that you see in the mirror is nothing but the virtual image but not the real image. So, the distance of the object from the pole of the mirror is said to be the object distance, and the distance of the image from the pole is said to be the image distance, which is indicated with the letter V. V refers to image distance. Image distance. Now onwards, whenever I use the letter U, it refers to object distance. If I use the letter V, it refers to image distance. From geometry, what I can say? If you see this angle, if I take it as alpha, this being 90, this is also 90, this is I, this is 90. If this is alpha, this is I, this is 90, means this is also alpha. That means this triangle OMP, and triangle MIP. They are similar triangles. Here triangle OMP and triangle MPI. These two are similar triangles. Therefore, what I can say, distance OP distance should be equal to distance PI. So therefore, this implies object distance U must be equal to image distance V. Modulus signs that their magnitudes. So for a plane mirror, object distance is always equal to image distance. That means when you are standing at a distance of 3 meters from the plane mirror, your image will be formed 3 meters inside the mirror. Suppose if you are at a distance of 1.8 meter from the plane mirror, your image will be at a distance of 1.8 meter inside the mirror. That means object distance is always equal to image distance when you keep a point illuminated object on the principal axis like this. Okay. So for a plane mirror, object distance is always equal to what? Image distance. For competitive part of exams and 1 and 2 mark questions, this is important point. Is it clear? So from similarity of mirrors, I can say that for a plane mirror, object distance is always equal to the image distance. Understood this point? And now, the incident rays, they will carry the information about the object, and the reflected ray will carry the information about the image. So what the incident rays will do? They will carry the information about the object, while the reflected rays will carry the information about the image. Now, here the incident beam is diverging beam, whereas the reflected beam is also diverging beam. The reflected beam, actually this reflected beam is originated from O, and even this reflected beam is also originated from O, but the reflected beam appears to originate from I. So the point where the reflected rays will really meet or appear to meet will give the image. If they really meet, they will give the real image. If they appear to meet, they will give the virtual image. So here the plane mirrors are forming which kind of images? The plane mirrors are forming the virtual images. So for a real object, we will be getting the virtual image. So in JEE level question, is it possible for a plane mirror to form a real image? Yes, provided the object is virtual. That means a opposite condition. For real object, virtual image. For virtual object, real image. So that is about the plane mirror. For a plane mirror, object distance is always equal to image distance. Now if I differentiate this function with respect to time, rate of change of object distance is nothing but object velocity. Rate of change of image distance is nothing but image velocity. Therefore, I can say that velocity of object is equal to velocity of image. Velocity of object in terms of magnitude is equal to velocity of image. That means if I am running towards a mirror with a speed of 3 meters per second, my image will also run with a speed of 3 meters per second, but in opposite directions. When you move towards the mirror, your image will move towards us. That means, so here in this case, object movement and image movement will be in opposite directions. Therefore, regarding the mirrors, what I can say means the velocity of the object is equal in magnitude to the velocity of image. Velocity of object is equal to velocity of image in terms of magnitude, but opposite in direction. That means if you are running towards a mirror with a speed of 6 meters per second, what is the velocity of your image? Again, it is 6 meters per second only, but opposite in direction. That means if you are moving towards the mirror, your image will move towards the mirror. If you move away from the mirror, your image will also move away from the mirror. So this is about the formation of image by a plane mirror. We are learning about the formation of image by a spherical mirror. Before studying about that, first we will calculate about the focal length of a spherical mirror. Focal length of a spherical mirror, which is important for the 3-mark question. So what are the sign conventions that we are adopting while you are dealing with the ray optics? Means all distances must be measured from the pole. All the distances must be measured from where? From the pole. Whether it is object distance, image distance, whatever it may be. All the distances must be measured from the pole. Distances measured in the direction of light ray are positive. Distances measured in a direction opposite to light ray are negative. Distances measured above the principal axis are positive. Distances measured below the principal axis are negative. These are the sign conventions. According to that, if you see here, this is the pole and this is the object. Light ray, incident rays are going like this, but distance is measured like this. So you are measuring the distance in opposite direction. Therefore, object distance is negative. Here u is negative. U is negative. Whereas image distance, this is image, this is the pole. From pole to image, this distance is measured like this, incident light is coming like this. So therefore you have to take image distance as positive. V is positive. Okay, using sign convention I can say that U is negative and V is positive. Understood? Now we will learn about the formation of focal length of the spherical mirror. We will study now. So the next topic is focal length of spherical mirror, or show that the focal length of spherical mirror is equal to R by 2 they will ask. For 3 marks they will be asking this question. Recently in previous board examination they have asked this question for 3 marks. Show that the focal length of spherical mirror is equal to R by 2, where R is the radius of curvature, Fm is the focal length of the mirror. First we have to know what is meant by a spherical mirror, what is radius of curvature and what is the focal length definition. Focal length definition means what? Suppose let us consider this is a curved surface. This is a curved surface. Now if I extend this curved surface, what I am going to get? I am going to get a spherical surface in 3 dimensions. This is a curved surface I am choosing first. This is the curved surface. If I extend this curved surface, I am going to get a spherical surface in 3 dimensions. This is a spherical surface. Now what is this curved surface? A curved surface is nothing but a part of a spherical surface. Yes or no? What is the definition of curved surface? A curved surface is nothing but a part of a spherical surface. So a curved surface is nothing but what? A part of a spherical surface. Now if this curved surface is silvered on one side, you can silver it inside or you can silver it outside. If I silver it inside, I am going to get a spherical mirror which is convex, or this is said to be the convex spherical mirror. If I silver it inside, suppose if I silver it inside, you will be getting a convex spherical surface. Instead of silvering inside, if I silver it outside, then I will be getting a concave spherical surface. Okay. So if convex shape is silvered, you will get a concave mirror. If concave surface is silvered, you will get convex mirror. Okay, now so a spherical mirror is nothing but it is a part of a spherical surface. It is a part of a spherical surface with one side silvered. Now for this spherical mirror A, P, B. If AB is a spherical mirror, here P is the geometrical midpoint. If P is the geometrical midpoint, I can say AP is equal to PB. Now the geometrical midpoint of the mirror is said to be the pole. Pole is nothing but the geometrical midpoint of the mirror. Now for this spherical surface, there will be a center. That is called center of curvature. What is center of curvature? The center of the spherical surface of which the given spherical mirror is a part. The center of the spherical surface of which the given spherical mirror is a part is said to be the center of curvature, indicated with the letter C. Now a straight line passing through center of curvature and pole. A straight line passing through center of curvature and the pole is said to be the principal axis. What is principal axis? A straight line passing through the center of curvature and the pole is said to be the principal axis. Now what is this distance? This is nothing but the radius of the spherical surface. Yes or no? The radius of the spherical surface of which, what is this? R is nothing but radius of the spherical surface. The radius of the spherical surface of which the given spherical mirror is a part is nothing but radius of curvature of that spherical mirror. So what is the radius of curvature of the spherical mirror? Radius of curvature of the spherical mirror is nothing but the radius of the spherical surface. Radius of curvature of spherical mirror is nothing but what? It is the radius of curvature of the spherical mirror of which the given spherical mirror is a part. Understood these things? Now when a parallel beam of light is incident on the mirror, then the reflected rays will meet at a particular point. The point where the reflected rays will meet is said to be the focal point or focus, principal focus. So, when we will define focus means or the principal focus means the incident beam on the mirror must and should be paraxial. Paraxial means the rays which are parallel to principal axis. The rays which are parallel to principal axis are said to be paraxial, parallel to axial line. When a paraxial beam of light is incident on a mirror, then the point where the reflected rays either meet or appear to meet is said to be the principal focus. So, we are having two principal focuses. Okay. So, now here it is a real principal focus. For concave mirror we are having a real focal point, whereas for convex mirror we will have a virtual focal point. Okay. So, what is principal focus means? When a parallel beam of when a paraxial beam of light is incident, when paraxial beam of light is incident on a spherical mirror, then the point where the reflected rays will meet is said to be the principal focus, and the distance from pole to the principal focus is said to be the focal length of the mirror. Focal length is indicated with the letter small f, focus with the letter capital F. The distance from pole to the focus is said to be the focal length. What is focal length of a mirror definition? The distance between the focal point and the pole. The distance between the focal point and the pole is said to be the focal length of the mirror. Is it clear? Now, we will go with the calculation of focal length of a spherical mirror. In order to calculate the focal length of the spherical mirror, first we need to choose a spherical mirror. Here I am considering a concave shape of spherical mirror like this. This is a concave spherical mirror. Concave spherical mirror I am choosing. Concave spherical mirror means convex side must be silvered. So, concave spherical mirror means which side is to be silvered? Convex side is to be silvered. Now, let me take AB is a spherical mirror. AB is a spherical mirror. For this spherical mirror, there will be a pole. Let me choose this is the pole. This is the pole of the spherical mirror, from where all the distances are to be measured. Now, for this spherical mirror, there will be some center of curvature. Let me choose here the center of curvature is there for this spherical mirror. This is the center of curvature C. Now, draw a line, straight line passing through center of curvature and the principal pole. The straight line joining the center of curvature and the pole is said to be the principal axis. Principal axis. Yes or no? Now, I want to calculate what? Focal length. If I want to calculate the focal length, I have to choose a paraxial beam of light rays. Paraxial beam of light rays means light rays parallel to the principal axis. Therefore, treat the light rays which are falling on the mirror as parallel beam. So, what I am choosing here, a parallel beam of light rays are incident. A parallel beam of light rays are incident like this. So, I am choosing this is one light ray and this is another light ray. The only two light rays I am taking so that you can understand in a better way. Now, what I have taken I will write here. In order to calculate the focal length of a spherical mirror, first we have to choose a spherical mirror. So, consider a concave spherical mirror, a concave spherical mirror of radius of curvature, spherical mirror whose radius of curvature is R, whose radius of curvature is capital R, and its focal length is Fm. Now, what we have done here? We have incident a parallel beam of light, incident paraxial beam, incident a paraxial beam on the mirror as shown in figure. as shown in figure. Now, if you see here, this is the light ray which is incident along the normal line. Yes or no? For a spherical surface, radius represents the normal line. If it is a spherical surface, the radius is nothing but always it is perpendicular to the tangent. So, radius always represents the normal line to the surface. So, when a light ray is along the incident, along the normal line, it will undergo reflection along the same line. So, this is incident and this is reflected. So, angle of incidence is equal to 0 here, angle of reflection is also equal to 0 for this light ray. But for this light ray, it is incident here. Now, at this point, I have to draw the normal. Normal is nothing but what? Radius. Radius means it should pass through the center of curvature. Therefore, let me draw the normal line. This is going to represent the normal line. This is the normal line here. Okay. Now, this is incident ray, this is normal line. Therefore, the angle between incident ray and normal line is called angle of incidence I. Angle of incidence I. Now, this incident ray must and should undergo reflection. While it is reflecting, according to laws of reflection, the angle of reflection must be equal to angle of incidence. Therefore, the reflected ray should come like this, making the same angle with the normal line. Making the same angle with the normal line, it should come like this. Now, what we are having? This is one incident ray and this is another incident ray. This is one reflected ray and this is another reflected ray. This is the point where the two reflected rays are meeting. So, the point where the reflected rays will meet when a paraxial beam of light is incident is said to be what? Focal point. So, this is the focal point or principal focus. Okay. It is said to be the focal point or the principal focus. Now, according to geometry, this angle and this angle must be equal because these two are alternative angles. If you are having two light rays like this, if this is I, this must be I. So, this is being I, this must be I. Yes or no? Now, drop a normal here from the point N on to the principal axis. Choose this point as P dash and this point as some M. Okay. Now, this is I, this is I. This point is C, this is F, this is M, this is P dash. Now, here how many right angle triangles are there? If you observe the diagram carefully, we will be having two right angle triangles. Let me take this angle as some alpha. Okay. Now, how many right angle triangles you can see? C, M, P dash is one right angle triangle, F, M, P dash is another right angle triangle. So, we are having two right angle triangles. Yes or no? Now, choose the two right angle triangles. Two right angle triangles are there, you take two right angle triangles. It is your choice which right angle triangle you want to take first, that you can choose first. Now, I have to use the geometry in order to find out this formula. Fm is equal to R by 2. So, for that what I am doing means, from right angle triangle C M P dash, C M P dash, I will take that C M P dash, I will draw here. This is C, this is M, this is P dash. This angle is I. So, what is tan I from this? Tan I is equal to opposite side MP dash divided by CP dash. Yes or no? MP dash by CP dash. Okay. But in optics, here we are treating the mirrors to be small mirrors. Therefore, the point M is close to the point P. When M is close to P, then P dash will approach P. So, when M is close to P, P dash will approach P. If P dash approaches P, or when M approaches P, I is tending towards 0. If I tends to be 0, tending to 0, not equal to 0, then for small angles of theta, sin theta is equal to theta and tan theta is equal to theta. This is a very important mathematical thing that we have to remember. For small angles of theta, tan theta is approximately equal to theta. M being close to P, for your understanding only I have drawn the picture to be large enough. Actually, this is a small mirror. Small mirror, this is being small mirror, M is close to P. If m is close to p, I tends to 0. Therefore, I is small. I being small, tan I is approximately equal to I. Is it clear? Now, for small mirrors, as m approaches p, as m approaches p, p dash approaches p, and I tends to 0. Therefore, for small angles, what I can say? For small angles, tan I is approximately equal to I. That implies, therefore, I is approximately equal to, here from this one, from equation 1, what I can say? MP dash is nothing but MP, and CP dash is nothing but CP, using equation 1. Take it as equation number 2. Okay, understood this point clearly? Now, from triangle CMF, if I take the triangle CMF, from triangle CMF, this is which angle? From triangle CMF, from triangle CMF, what I can say? CMF triangle, if I choose, this angle is I, this is what? Alpha. Here, exterior angle is equal to sum of opposite interior angles. From mathematics, we know that exterior angle is equal to sum of the opposite interior angles. Therefore, what I can say? Alpha is equal to I plus I. I plus I implies alpha is equal to 2I. Take it as equation number 3. Now, already we have chosen one right angle triangle, another right angle triangle is remained. Which right angle triangle we have chosen? CMP dash is chosen. Now we have to choose FMP dash. Now, from right angle triangle FMP dash, what I can say? Let me draw FMP dash first. This is F, this is M, this is P dash. This is alpha. So here I have taken CMP dash, I applied tan I. Now I have taken FMP dash, applied tan. What is there here? Alpha is there. Tan alpha is equal to what? Tan alpha is equal to what we are having here. Opposite side MP dash divided by FP dash. But alpha is small. Therefore, what I can say? Tan alpha is approximately equal to alpha. That is, tan alpha is equal to this MP dash is replaced with MP. Why? Because MP dash is M approaching P, P dash approaches P. Therefore, MP dash is approximately equal to MP and FP dash is equal to FP. Okay. Now, what is alpha here? Alpha is equal to 2I. This implies alpha is nothing but 2I. 2I is equal to MP divided by FP using equation 3. Now, this is equation 2, this is equation, you take it as 4. Okay. So, what I have done? Alpha is there, alpha is nothing but what? 2I. I have chosen alpha is equal to 2I. So, alpha is equal to MP by FP, therefore, 2I is equal to MP by FP. Now, from equation 2 and equation 4, what I can say? From equation 2 and equation 4, what I am having? 2 into I means what here? MP by CP. MP by CP is equal to, what is this? MP divided by FP. MP divided by FP. So here MP will cancel on both sides. then 2 divided by Cp is equal to 1 divided by Fp. Now you see here, what is this Fp here? Fp is nothing but what? This is nothing but focal length of the mirror, Fm. And what is Cp? Cp is nothing but the radius of curvature, which is equal to r. Here r is negative. Why? Because we have to make the measurement from the pole to the center. It is light ray is coming like this, pole to center distance is like this, opposite direction, therefore r is negative. Even Fm is also negative. Pole to focus is negative here. So focal length of the concave mirror is always negative. So substituting these values, what we are getting? Using sign conventions, we have, what we are having here? We have Cp is equal to minus r and Fp is equal to minus Fm. Take it as equation 5. So from equation 5, what I can say? Now, therefore, from equation 5, 2 by Cp is nothing but what? Minus r is equal to 1 by minus Fm. Minus will cancel on both sides and we are remained with 2 by r is equal to 1 by Fm, implies Fm is equal to reciprocated. Reciprocating this, r by 2 we will have. So focal length of mirror is equal to half of radius of curvature. Focal length of mirror is equal to what? Half of radius of curvature. If focal length is if radius of curvature is equal to 15 centimeter, what is the focal length? 15 by 2, 7.5 centimeter. If radius of curvature is equal to 30 centimeter, what is the focal length? Focal length is equal to 15 centimeters. 15 centimeter. If radius of curvature is equal to 60 centimeter, what is the focal length? 60 by 2, that is 30 centimeter. Important for 2-mark problems. And one more thing you have to remember here means focal length of concave mirror is always negative, while the focal length of convex mirror is always positive. Focal length of concave mirror is negative, while the focal length of convex mirror is positive. This is important for your 3-mark questions. Okay. So this is about your today's class. In the next class, we will study about the mirror formula.